All right, so last lecture today in kinetics, we're talking about how temperature affects reactions, and today Ms. Rozier sent this to me. I thought it was really funny and pretty appropriate for today's lecture. So this is a little bit of a description showing the differences between the different temperature scales. It's pretty entertaining, and it's very true. So there you go, if you ever wondered. Yeah, I think it's hilarious. Y'all are very quiet and don't seem... Okay. Thanks for that sarcasm there, Ishan. Appreciate it. Okay. Well, I didn't even hear those, so they weren't very pronounced. It's okay. You don't have to laugh at my jokes. That's cool. All right. So a couple of things that are going to show up on the AP and most definitely on the test because it just got written yesterday. It's the ability to draw diagrams and then interpret diagrams. These diagrams that I'm about to show you are super important because they are showing you the direct correlation between changes in temperature and reaction rate. So if you look at both of these pictures, and what I want you to focus on is the need to remember what goes on different axes. We're going to look at how temperature affects reaction rate. So this is looking at the same reaction and done at two different temperatures. Now, I'm not real thrilled with this picture. We really theoretically should have a much higher thing here because the area under the curve should be the same in both pictures. Because what I want you to think of, the area, I want you to think of it as the number of molecules because that's what's on the y-axis. So this reaction is just happening when we are at a low temperature of 300 Kelvin versus a higher temperature of 400 Kelvin. That little hash mark right there, that represents the activation energy. Notice how it's in the same location of both pictures. If you change the temperature of a reaction, you don't change the reaction's activation energy. That's the energy required to get the reaction to start. What does happen, though, notice at this cooler temperature, as we heat it up, the molecules will shift to the right. Meaning, here we have very few molecules that have enough activation energy to react. Here we have all of these molecules that now are at the appropriate activation energy. More molecules, more collisions, faster. So this is the faster of the two. Heat them up, speed them up. And this is a graphical representation of why. So if you're asked to indicate what happens in temperature changes, this is the kind of diagram we're looking for. Not only is it on AP exams, when I got nationally board certified, this was like the question, and I was laughing because I was like, I do that with my students, no big deal. But it's apparently a big deal to everyone. So make sure you know what goes on your axes and kind of the drawing. Do y'all understand it? Okay. Now what happens in a scenario where we have a reaction, but now we add a catalyst? How is that going to deal with? Again, this is number of molecules. And what goes on the Y? The energy, right? And this is energy. So when you add a catalyst, you don't change temperature. You don't change delta H. Very little of the reaction changes. But what does change when you add a catalyst? Myra? Yeah, the activation energy changes. It lowers. So which of these two is your catalyzed reaction? The second one. This is catalyzed. And this is uncatalyzed. Why that is, here we have a higher activation energy where that line is. When we catalyze it, the activation energy is literally lowered. So that allows more molecules to have the appropriate activation energy to react. If I'm looking at an energy profile, well, I'll do it on the next page because this is one kind of diagram that you're expected to be able to do. This is just a prettier version of the same picture. This was done with like one of those Apple computers from the 1980s. Those box computers. Y'all ever seen those with a floppy disk drive? Yeah. And then this is today. Yes? Why does the amount of molecules what? It's a Boltzmann distribution. So as reactants, the more energy you have, more of them have energy. It just makes, I mean, it's not I don't want you to think of it as a curve. It's not like a function. This is literally molecules with different energies. So anytime we're plotting a relationship, I mean, it could technically be like this. I mean, it's not perfectly curved, but it represents physically how many molecules here and how many molecules are there. So focus more on the area under the curve than the actual, don't look at it as a function. Okay? Anyway, moving on. Catalysts. Speaking of catalysts, now we talked about them a little bit. We do want you to know a little bit about catalysts, and there's two catalysts we need you to know about, heterogeneous catalysts and homogeneous catalysts. We're not going to test you a lot about these. I just need you to know they both kinds exist. Heterogeneous catalysts most often occur with gaseous reactants on top of a solid surface. So what a catalyst of this kind allows you to do, it allows gas molecules to come in, adhere, getting them close together enough so they can react, and then releasing them. The catalyst just provides that surface that brings things closer together. This is called heterogeneous because this is in a solid phase and that's in a gaseous phase. So you could have a solid and a liquid, whatnot. Heterogeneous are usually, they're always in different phases. That's why they're called heterogeneous. And so their primary function is to provide a place, a docking station, you can say, where you're allowing these molecules to stand still for a second, get close together, get oriented appropriately so a reaction can happen. Okay? This is just another picture of kind of the same thing, absorption and release of products, absorption of catalysts, of reactants, and release of products. And notice that the catalyst comes out the same as it was at the beginning, at the end. Okay? The other kind of catalyst is the one that you guys are more familiar with, and it's the homogeneous or homogeneous catalyst. It's the whole lock and key model with enzymes, and you talked about this in biology probably, where this catalyst is actually part in the same phase, comes across as part of the reaction, where you can't tell necessarily just by looking that there's a catalyst there, but I'm looking at the solution from our perspective. But what happens here on the molecular level, you have that lock and key model where your substrate comes into the active side of the enzyme, and reaction occurs, and then release, leaving the catalyst from the beginning to the end coming out exactly the same. It's homogeneous because this is in the same state of matter. Okay? It's actually all tied up. It's all tied up with your reactant molecules. Okay, so that's all I need you to know about catalysts. This is another kind of diagram that you need to be able to do. This is your energy profile, where here, you've seen this since Chem 1. You have reaction coordinate, which means progression, basically, of reaction. Reaction progression as well on the X. On the Y is energy. So if you have energy on the Y-axis, your reactants are going to have a particular energy. Your activation energy from reactants to the tippy top is going to be a certain value. And then you can find delta H, change in energy, delta H or delta E, by finding the difference between the reactants and products. Is this exothermic or endothermic? Yep, this is exothermic. Heat was released. We had high reactants, low energy products. The heat had to be released to get there. So you need to know how to draw one of these. You've got some good practice homework problems on this. At the very tippy top, the activation energy from reactants to products, we have something called the activated complex. The activated complex is basically this transitional molecule that occurs when the molecules have enough activation energy, and it's the transition between reactant and product. It gets like this not really bonded, but sort of bonded, really high energy complex. Super unstable, so it's going to quickly go to products. But when we say activation energy, that's what we are measuring. We're measuring the activated complex energy. or the transition state energy. Okay? One thing to consider is that these reactions can go forward and reverse. If you go reverse, what would be the activation energy of the reverse reaction? Okay, you could look at it that way, delta H plus E of A, but this would be the activation energy of the reverse. Okay? Would delta H change of the reverse? It changed signs, but it doesn't change its magnitude. What else do I want to say? Oh, and if I add a catalyst, what does the catalyst do? It lowers this hump. The hump just makes the reaction occur a little bit faster because it's a shorter pathway. Did that change the delta H? That's hugely important. Adding a catalyst never changes the heat of the reaction. Okay, so be able to draw these, be able to interpret them. They're not difficult. You'll probably see this, probably. Okay. Next and final is collision theory. Collision theory is hugely important. There are two things that are required to make a reaction happen. Two things. The reactants have to have enough activation energy. That's the first. They have to have enough energy to get to the top, right? That transition state. The next thing, reactants have to collide in the appropriate orientation. Okay? So those of you who had me last year already heard me say this, but I think about it every time I talk about collision theory. In the summer I teach teachers, and I was teaching way deep in West Texas somewhere where there's nothing. I don't even think I had cell service, like deep, deep, deep West Texas. And we were talking about, I have discussions with teachers on how they want to teach things, you know, to appeal to their students, all that kind of stuff. So one lady was like, when she teaches, they have like 4-H and all these great cattle, whatever stuff going on. So she teaches us talking about how cows make babies. So think about that. The bull has to have enough energy, right, to get where he needs to get. That's not easy. Think about it, right? And then he obviously has to be at the right orientation. Duh. Or so, there you go. That's two requirements. Please do not use that analogy on the AP. So there you go. Enough energy, right orientation. Don't you dare put my name to that. Don't you dare. You will ruin my career as an AP grader. Okay, so anyway, remember those two things. Remember the cows. So here, is an equation that represents collision theory. This is called the Arrhenius equation. You do not need to memorize this. We're showing it to you because, well, it's an important equation because it's the only way that we really use to actually get a numerical calculation for activation energy. We can actually find the value of activation energy using this equation. Not in this form, but I'll show you the form in a second. So this equation has some factors in here. This is the orientation factor. We talked about that. The easier something orients, the more options it has, the higher this value. The higher that value is, the bigger the K. The bigger the K, the faster the reaction. And when I mean K, I'm talking about the K in a rate law. And that's not, I'm going to use X here. I don't want you to think that's the same A. So there's a direct relationship between K and rate. So if we double the K, we double the rate. Easier orientation, more collisions. Our K is going to be higher. If this is higher, K is higher. Okay? The more energy something has, the easier it is then to collide. Therefore, the higher the K, the higher the rate. And activation energy is taken into account right there. And this is a negative exponent, so that's why the bigger it is, the higher the activation energy. The higher the activation energy, the lower the rate because of the negative. Yeah? Okay. All right. So don't memorize it. But what I'm going to do, show you some manipulations with that. If we were to take this, first off, I want to go this direction to here. This is this equation above linearized. How did we get from the top equation to the bottom? What happened? It's really simple what they do. Yeah, they natural log both sides. They got ln of k, and then if they take the natural log, it brings this down, leaving ln of a, right? This, you saw yesterday how much we like to linearize stuff in chemistry. It's very, very common. So I want you to write this. You don't have this equation down, but I want you to write it like this, a little bit differently. ln of k is equal to negative EA over R times 1 over T plus ln of A. If you write that down, we are again in a situation that we can use a graph to find something. First period let me down a little bit. They didn't remember at all what I was talking about. But you guys did a lab using the Clausius-Clapeyron equation, and you found the heat of vaporization by plotting things a certain way, and then you took the slope and you multiplied it by R. This is going to come out to be the exact same thing. But what did we plot? Let's just do a little remembrance of the Clausius-Clapeyron. What did we plot? It was 1 over temperature, but what did we take the natural log of then? What did the lab do? It was an online lab, pressure, right. You took the natural log of pressure, you plotted it, and then you multiplied the slope by negative R, right? And you got the heat of vaporization. This is almost identical, except here we're taking the natural log of K values. So they're coupling a temperature with a K, because Ks are temperature dependent. So by K I mean rate constant. So we plot our rate constants on the Y and 1 over temperature on the X. We're going to get a line. And what's the slope of that line equal to? Yep, so we do the same thing we did before, where we multiply the slope of that relationship times R. I don't want you to memorize the equation, but I do want you to know what you would have to plot to get activation energy. Okay? All right, where that comes from is the Arrhenius equation. This guy came from what we called Clausius-Clapeyron. I don't expect you to know the names, but if you hear them, if they show them to you and bring in those names, I want it to not scare you. Okay, so then what they decided to do, remember with Graham's law that we had that law of the gases and the rates of gases is equal to the ratio of the molar masses. That was a big square root thing, remember? That was derived by just taking the root mean squared velocity and making it a ratio with another root mean squared velocity. And that's how well, this is the same thing. They derived this by taking one temperature and K relationship and then putting two equations, making a ratio, and this is what they came up with, a combined equation. What's really cool about this equation is we don't have to find a whole bunch of data points. All we have to do is know two temperatures and two Ks associated with that, and we can calculate the activation energy. And it's based on this linear relationship. So if I ask you to do this, you'll be given this equation. Don't memorize it. So an equation can be used in a problem like this. At 300 degrees Celsius, the rate constant is this. At 400, the rate constant is this. Calculate the activation energy. That's just plug and chug. The thing you have to be careful with here is make sure you pair your Ks and your temperatures together. So I'm going to put this temperature and K together. This will be my first set, and then this will be my second set. Remember, R on the last page it told you was 8.314 joules per mole Kelvin. So what would be something that would be good to do right now? Yeah, we need to convert to Kelvin. So we're going to make this 573 Kelvin, and we're going to make this 673 Kelvin. So now all we have to do literally is plug and chug. So natural log, K1 is 570, no, 2.41 times 10 to the negative 10th divided by K2, which is 1.16 times 10 to the negative 6. That's equal to, we're looking for the activation energy. This is 8.314 joules per mole K. 1 over, what is my T2? 673. My T1, 573. So all I have to do now is solve. The negative canceled out on that EA when you multiply through. So activation energy, can it be negative or should it be positive? Positive, why? Right. Those reactants need energy put in to give them the appropriate energy. They're not going to, on their own, climb a hill and give off energy at the same time, okay? So overall, our reaction, our delta H or our delta E of a reaction could be negative, but not that original activation energy. Yeah? I don't care unless I tell you. So what is it going to be, though, when you calculate it? Joules or kilojoules? 272,000. So that would be 272 kilojoules. I don't worry about making a change unless you're asked. Leave it in joules. Is everyone happy with that answer? Okay. No? Yes? Okay. This last problem again, super simple using the same equation, except this time we are looking for a temperature change. I like this problem because you have to make some assumptions, which I think you need to understand why we're making. If the activation energy is something, so we have that, calculate the temperature change necessary to double the rate at room temperature. So room temperature is what in Kelvin? 298, good. Everyone yelled out 273, and I'm like, nope, that would be really cold. 298. So we are looking for a relationship. To find the delta T, I need to know both of these, and I could subtract them, right? So I'm going to pretend this is T1. I want to double the rate. Remembering that relationship, if I want to double the rate, will doubling the K work? Right. So what could I do here? I don't have any Ks, but I know it needs to be doubled. Use 1 and 2. I want K1 and T1 to be the couple, right? You got to couple them the same. If you increase the temperature, the rate is doubled. So this is going to be 1 over 2 equals E of, oh, they've given me E of A this time. Uh-oh. It's in kilojoules. I got to convert that. So it's 1.0 times 10 to the 5th joules per mole divided by 8.314 times 1 over T2 is what I'm solving for. And 1 over, why did I write T? 1 over 298. So I'm going to solve for T2, and then I'm going to subtract them to get the delta T. They have a rule of thumb, and this shows you that the rule of thumb is bad when you see this. There's a rule of thumb that says every 10 degrees you double the reaction rate. Sure. Let's see if that's true here. Anybody get one? I know the answer. Would you? Yep. 303K. So T2 came out to be 303. So this is a 5-degree difference. So when we double the reaction, when we change the temperature by 5 degrees, this doubled the reaction rate. Any questions about anything? That's kinetics, my friends. That is the last part. Okay, have a good day.